in previous session, we discussed about application of quantum mechanics. We saw few tools like Julia. Today, I will give a easy and simple tool for you, which is called QBrain. Okay. So I will share that link with you. I will share that link with you. All of you go to this tool called QBrain. So click this link. This will lead to QBrain. So this is one-stop solution for all your quantum computing platform. If you're using Qiskit, Google Circ, or Microsoft QSharp, or Pennylin, so this one tool will, one platform will help to run all type of quantum tools. Okay? So I highly recommend this tool because it will make your research easy, simple. So most of the time, what happen if you want to install new version of your quantum software tool, each and every time you need to uninstall and reinstall. Okay, but without having any hesitation and hurry, you can install multiple kernel in a common platform. Okay, so the installation and maintaining your software become much more easier, especially if you are from non-CS and IT background. Okay, so if you have Gmail account, you can create a login. You can create a sign up. So I already created a login. Please try to rejoin. I have full voice. Full voice. So try to create an account. Try to create an account. You will get the dashboard like this. You can directly install Qiskit in your Jupyter notebook, or you can install in Google Colab, or you can install in QBrain. So try to create an account in this QBrain tool. So once you created login, if you are able to get this dashboard, please let me know. I'll give some time. I'll give some time. Create a login. Try to get this dashboard. Okay. Are you able to see this account? Plan free, launch lab. Okay, good. Good. So click the default workspace. Click the default workspace. Click next. Go to this link. Create login. Select launch lab. Default workspace. So you can take a note if you are not able to do so. You can take a note with pen and paper. Then select launch lab. Then select launch lab button. So what they are mentioning, they are offering 2 version CPU with 4 GB RAM capacity. So they are giving this credit online. Okay. So click launch lab. Click launch lab. So it will lead to a Jupyter notebook kind of environment, or you can see Google Colab kind of environment. So you can see this interface. where you can install multiple quantum tools by selecting environments. Okay, so if you want to install Microsoft or Google or QuizKit or PennyLane, you can click here. So click environment and browse environment. If you want to install any quantum software, click environments plus add button. So click add button, select QuizKit, So you can see any number of versions are there. Okay. So in QuizKit, you are able to see number of versions. Suppose if you want to run the older version of code, okay, the code is the application example written in older version of code, then you need to select 0.42.0. Otherwise, if you want to install the latest version, you can go for QuizKit version 2.2.1. So likewise, you can change your kernel accordingly. You can run any kind of coded version, not only the latest, also able to execute the older version of code. Okay, this tool I highly recommend for you. Okay, so try to install the latest version. So select here, try to install, click button. The latest version is installed. It will take some time. Once, if you are able to install, then let me know. So once you install, it will pop out over here. Once you install, it will pop out over here. Anybody installed QuizKit? Are you able to see like this? Default PennyLane QuizKit. Okay. So if install means what you can do, you can click a new notebook, go to file, click new, select new notebook. So this is one way to create your notebook. Otherwise, you can create from here. So Python 3 QuizKit version 2.0.2. So look at the chat box. Look at the chat box. That is why I'm putting in chat box. So click add button. Click add button. So step by step I'll give. Step 1, step 2, step 3. Maybe I'll type over here. Step 1, go to this link. Step 2, create a login using your mail ID. Step 3, select launch lab and try to select default workspace. It will take some time. Step 4, then select launch lab button, click that. Step 5. If you want to install any quantum software, you need to click environment, then click add button. It will list out the number of software tools supported. Step 6. Install latest version of QuizKit 2. What is that version? QuizKit version 2.2.1. I will copy paste in command. Yes, I installed little uh, little previous version. So latest is 2.2.1, which is supported by QBreak. Supported by QBreak. Are you able to follow now? Do slowly. Do slowly. Then what you do, if you want to click any new notebook, you can directly click here, Python 3 version 2.2.1. So in my case, it is showing 2.0.2. In your case, it will be 2.2. So click that. You can see kernel version over here. So likewise, you can play between the new version and the older version. So it will be easy for you if you want to execute any of your code. Okay. So go to this link. QuizKit in Classroom Quantum Mechanics. So today we will cover some of the topics. So I'll share this link with you. So go to this link and you can use whatever the coding provided in this website in your QBreak notebook. All of you able to get this link? So here they will say what are the tools you need to install. Okay, you already installed all these tools, so no need to reinstall again. Directly you can go for coding part. Okay, I'll copy this first command. I'll share in the chat box. Okay, so copy paste the same code in your QBreak tool. So try to run. You're able to see the output. Okay, select this version. So go to file, go to new, select notebook, select notebook. Once you installed your Qiskit version, you can select from here. So select this. So it will create a notebook along with the selected kernel. Okay, let me see. It is not showing error for me, but it is not displaying also. Okay, I try to install the new version. Then I try once again. Let's see what happened. Let's check. Are you able to see the output like this? I installed latest version also 2.2.1. So let's see. Select. I just try to copy paste this code alone. Yes, running. Latest version. Okay. So once you install, what you're supposed to do, you need to refresh your environment. So click and refresh your environment. Yes, it is not giving error, but whether it is giving output at least. Okay. Even for me, the new environment is not added, even though I install, not added. Okay. I will log out. I will re-log in. Let's see whether it is running. Discard. I log out. Just only one time. Once you created environment, you can run easily without any maintenance error. We cannot do anything because it is from their end. That is the problem. Okay. So this is the error you are getting. Okay. So many people try to attend. Okay. So before that, we will try to cover some topics. Before that, we will try to cover some topics. It is simulator, not quantum computer. It is simulator. Okay. So we'll discuss two important principles for quantum computing. Okay. So one is superposition and one is entanglement. So we'll refresh basics. Okay. So these two are fundamental pillars for quantum mechanics. Take an example of quantum superposition. Okay. So the quantum superposition can be happen in any quantum particle. A quantum particle could be photon, it could be electron, it could be ion, it could be neutron. Any subatomic particle can called as quantum particle. Okay. So normally, if you are looking at a quantum particle, it will spread out like a wave. Okay. Not like in the chemistry book, it is showing like a dot. Actually, it will spread out like a wave. So if you want to know its existence, if you want to describe its existence, okay, you need to use the wave of probability, like a wave of probability, right? So here, if if you want to describe the location of electron, you will have only 20% of chance. So here 30% of chance. Here 45% of chance. So actually, according to the location, you can describe with the help of probability. So it will not exist in a single place. It will exist in multiple place. It will exist in multiple place. Okay. A state of being in multiple location or multiple places at once, each with a different probability. So a quantum particle could exist in multiple places and also with different kind of probability. Okay. According to the place, the probability will differ. So if you have multiple waves in the water, if you want to form the resultant wave, what you're supposed to do, you need to add all water waves. So in the same way, a quantum particle could exist in multiple states. So if you want to define that quantum particle, then you need to add all quantum states to define superposition. Okay. In simple terms, superposition is one position over another position at the same time. Okay, this is the simplest explanation of superposition. Okay, so describing a quantum mechanics using quantum mechanical term, it will be difficult for us. We are not able to understand. For that, we are taking a classical example. Okay, so the classical example will help you to understand quantum mechanics or quantum principles. Okay, So take an example of coin. You are taking a coin and you are tossing that coin in the air. So during the air flip, okay, you cannot say what is the state of the given coin. So it is in mixed state. So it is in superposition state. So if you are looking a coin in the during the air flip, at the same time it will appear like a head and also it will appear like a tail. So what is the chance being a head? 50% of chance. What is the chance being tail? 50% of the chance. A coin contains two faces. So two faces equally divided into two different probabilities or equal probabilities. Okay. So when you can say a coin is a head or tail, when you try to stop that coin, okay, so allow that coin to freely fall over the ground, it will settle down. Then you try to observe and look at that. So it is a passive measurement. Okay. Suppose if you want to stop that coin by your hand, it is a active measurement. Okay, forceful measurement. When you do measurement, when you open your hand, you are able to observe the result. Okay. So during that time, what you are doing, you try to collapse superposition. So when you stop that coin, when you stop that coin, by your hand, forcefully, it is active measurement. This process is called active measurement. Okay. So when you open your hand, when you open your hand, what you are doing? You are doing observation. You are doing observation. So two things we are doing. What we are doing? We are doing measurement followed by observation. Followed by observation. Okay. So this is what happened. This is what happened. When you do so, the superposition will get collapse. The superposition will get collapsed. Are you able to understand the concept? We have a coin. Coin contains two faces, head or tail. During the air flip, it is in superposition. During the air flip, it is in the superposition. So two-way, you are able to do measurement. Allow that coin to freely fall down to the ground. When you are doing, that is called passive measurement. So if this coin is falling over the ground, it is a passive measurement. Okay. When you try to stop that coin by your hand, it is active measurement. So whatever the measurement is going through, okay, superposition state will get collapsed. Okay. So during the air flip, you have 50-50 chance. During the air flip, you have 50-50 chance. But when measurement happen, you will have only 100% of chance. Either head or tail. Tail also 100%. Okay. During the air flip, 50% of chance for head, 50% of chance for tail. So here it is and, okay, here it is or. That is the primary difference. I try to change the color. Now you can see it is and this is or. If you understand this example, you can understand this Schrodinger cat experiment. So we are taking a black box. We cannot see what is inside that box. Okay. So what we are doing, we are putting a live cat and we are putting a radioactive material. Okay. Nobody know when that radioactive material is going to decay. If that radioactive material is going to decay, the cat is exposed to that. If cat is exposed, the cat will become dead. Okay. So inside box, cat is being alive 50% and dead 50%. So it is the condition of and, or you can say both. A cat can be alive 50% chance, cat can be dead 50% chance. But when you try to open that box, what happens when you try to open that box? Open this box, superposition will get collapsed. Superposition will get collapsed. Okay, so what happens? This condition will turn into alive 100%, alive 100%, or dead 100%. So cat have multiple states. Okay, what are the multiple states? Either alive or dead. Inside that box, it is in superposition. When you try to open, what you are doing measurement operation. When you do measurement followed by observation, superposition state will get collapsed and you'll have only one of the possible outcome. Only one of the possible outcome. Okay. So try to go for little bit complex example. If you have a cube contains 6 faces. So each face colored with different color. Okay. So which color appears for you according to the angle and position where you are making your observation and measurement. If you are observing from this angle, orange appears like print. If you are observing from this angle, blue appears like print. So cube contains 6 faces. 6 faces turn into 6 equal probabilities. So 1/6 probability. This is 1/6. 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 But when you do measurement, okay, one probability will become 100%. One of the possibility. One of the possibility. Either orange is 100% or blue is 100%. So likewise, you can imagine 6 different colors. So each face contains 6 different colors. Okay. So try to correlate with an electron. Imagine electron like a cricket ball. It can spin upwards sometime. It can spin downwards sometime. So you're associating your value to spin of an electron. Suppose if the electron spinning diagonally, sometimes electron can spin diagonally. Like imagine a cricket ball could wobble. If it is wobbling, it is in superposition. It is in superposition. So this is a broad explanation of superposition. Okay. So if you want to explain all this stuff in classical world, it is more difficult, which is very, very more difficult to understand. Even though we don't have any choice, we are using classical example to understand quantum phenomena. Okay. So the next important topic is entanglement. So entanglement is like strong correlation between two quantum particles. So you can see under the right condition, this plant can grow to full potential. In the same way, under the right condition, if you are taking 2 electrons or 2 photons, if you are making in the entangled states, means strong correlation you are creating. Okay. So whatever happens for one quantum particle, it will impact the other quantum particle in the same way. In the same way. Because they are strongly correlated. Okay. So take an example of one particle. Take an example of one particle which is existing in air. Okay, the properties of two particles are related, even the particles are separated. So to do entanglement, you need to keep two quantum particles next to next. But once you create it, you are able to separate. You are able to separate to another universe or another galaxy or other satellite. Okay, so this is related to a beautiful quick game called rock, paper, scissors. So most of us we know, okay, 3 persons are playing rock, paper, scissors. So measuring one of the person instantly decides the state of the other faster than the speed of light, at least theoretically. Okay, if three persons are playing rock, paper, scissors, instantly you able to know who is the winner, who is the loser, right? So the entangled particle can influence each other's states even if they are separated galaxy apart. Okay, so we are taking two quantum particle. It could be electron, it could be photon, it could be ion, it could be any subatomic particle. And what we are doing, we are trying to make strong correlation between them. After doing strong correlation in laboratory, we try to separate. So once you separate quantum particle, whatever you are doing for one quantum particle, let's say this is P1 and P2, photon 1, photon 2, photon 1, photon 2. And what you are doing, you are turning your photon to downside. So this is downside. You're turning your quantum particle P1 to downside. What happens? The P2 also matches. The P2 also matches. It is also pointing to downside automatically. Automatically. So what happens when you try to move this quantum particle to upside? Now imagine it is moving to upside. So this quantum particle also move to upside. It is matching with particle 2. So whatever you are changing, the entangled particle also move in same direction. To understand this, it is like a black magic. So whatever happens for one, it will immediately impact the other quantum particle without any delay. So this principle we are using for quantum computation, not only computation, we are using for quantum communication. Okay, imagine here it is pointing to 0. It is pointing to 0. This also pointing to 0. This also pointing to 0. Both are changing means instantly it will correlate to each other. Instantly it will correlate to each other. Imagine both are synchronized. Imagine both are synchronized. Is it clear? The changes will happen with speed of light, faster than speed of light. Is it clear now, Rahul sir? We will cover that. We will cover that. We will cover that. So wait for a minute. Wait for a minute. So scientists able to do experiment, they are not able to understand why it is happening. So in 1935, Einstein denied this concept. So Einstein don't want to accept this factor because for him it is like a spooky action at a distance, like a black magic. So Albert Einstein is scientist. He was not able to reason why it is happening. Okay, so any correlation would have to be predetermined. Predetermined. He was not able to understand this. Okay, so he argued it is a predetermined outcome. Predetermined outcome. Okay, so he cannot able to understand. He cannot able to understand the instantaneous change happening in between two particles. Okay, they able to observe but not able to realize why it is happening. So for a scientist, there is a strong demonstration is needed to accept that principle. So during that time, they are not able to demonstrate. They are not able to demonstrate. Okay. So these are the famous reaction to quantum mechanics. If quantum mechanics hasn't profoundly shocked you, you haven't understood it. Said by Niels Bohr. Suppose if you are watching so many classes in QT-01, 02, 03, 04, even though if you have difficulty in understanding quantum mechanics, it is just normal. Okay, just normal. Okay, don't worry too much. And one more interesting saying quoted by Richard Feynman, one of the Nobel laureate. Okay, Nobel laureate. I think I can safely say that no one can understand quantum mechanics. So these are the words spoken by world-renowned scientists. If it is hard for them, definitely it will be hard for us also. Okay. So sometimes it will confuse you. Sometimes you are not able to understand. You are the already learning concept. It will counterfeit when you try to learn quantum. That is the problem. If you cross 30, 35, 40 or 40 plus, it is become more difficult for us to learn quantum mechanics. Okay. So Erwin Schrödinger quoted, "I don't like it, and I am sorry I had anything ever to do with that." So it is not normally said by a simple person, layman person. The people who are interested in quantum mechanics, they try to work on that. They tried very hard. After some point of time, they desperately fail to understand the quantum mechanics. Exactly, exactly. So there is a famous scientist called Scott Aronson. So if you want to understand, yes, definitely, we are in 40. That is why we are struggling. For juniors, for school students, for undergraduate students, it is quite easy for them. It is quite easy for them. Okay. So Scott Harrison is a famous professor in MIT. If you have time, go and visit his website. He's teaching quantum mechanics in MIT. So you can compare quantum mechanics is like operating system that all other physical theory running on as an application software. So whatever the physical theory we have right now, so all this physical theory is operated over quantum mechanics. You can imagine like quantum mechanics is like real operating system of nature, true nature. A very beautiful portrait about quantum mechanics. So we can ask the basic question, why we need to understand the quantum mechanics and what it is very good for us. Okay. So quantum mechanics is very good for developing lasers, powerful lasers. So in future, the warfare will become entirely new. From the satellite, they able to demolish any place in Earth. So it is also possible. Okay, like Star Wars. Okay, in future, scientists able to create laser-based weapons, which is very precise and most dangerous when compared to traditional or conventional equipments, and it will lead to nuclear reaction. Suppose if you want to create a powerful nuclear bomb or atomic research, okay, the development of quantum mechanics will lead to clean energy and green energy. Okay, so when you compare to fossil, nuclear energy is somewhat cleaner. Okay, so some people may argue nuclear power plants are very dangerous. Okay, so any technology is very dangerous until or otherwise how we are handling them. So if we are handling with uttermost care, so it is always safe, always safe. And quantum mechanics will help you to design better transistors. If people are from EC and EEE or instrumentation and control, they like to create a better transistor. Okay. Not only for digital, if you go for neural network, if you go for analog computing, transistor will play a vital role. Okay. So if you want to build better transistor, you need to understand quantum mechanics in better way. So these are the justification about today's topics. Right. Not only for these three, and especially in future, for medical devices, quantum mechanics will play a vital role. If you want to improve your device accuracy, okay, only the quantum mechanics based medical devices will give very accurate results, like molecular level. If you want to treat patient at molecular level, the quantum mechanics based medical devices, scanners, they will help us. So I'll skip this slide. I hope we covered control NOT gate in previous class. Control NOT gate. It is a quantum phenomenon. Superposition entanglement, quantum phenomena, quantum mechanics is quantum phenomena. Are we covered control NOT gate? Okay. So I'll refresh in quicker time. So control NOT gate, the first one is control qubit, the second one is target qubit. So after going through control NOT gate, your quantum state will get changed, Q1 dash, Q2 dash. Okay. So whatever you are giving for Q1, okay, whatever you are giving for Q1, it will impact Q2 according to the states. So 0 means there is no control. If there is no control, no change in Q2. So Q2 will retain as it is. Okay. So second case is Q1 is 0, Q2 is 1. Okay. Because Q1 is 0, Q2 will not get changed. So these two cases, no control. No control. Okay. If there is no control, the state will retain as it is. Q2 state will retain as it is. So look at the third case, what is happening? We are giving 1 in Q1. So what happens? This 0 is transformed into 1. So changes is happening. Changes is happening, right? Not to this one. I'll delete this, try to redraw. Okay, look at the fourth case. If Q1 is 1, okay, the Q2 is get altered, it is changed into 0. So this is the simplest example of control NOT gate. Okay. So recall the previous slide. We covered about entanglement, right? So somebody asked about the opposite reaction. Okay. So we talked about equal correlation. Whatever happens for P1, you can see the same effect in P2. So this is like synchronized. Okay, positive correlation. You can say equal correlation. Sometimes you can directly connect opposite side of a qubit with the another qubit. Okay. So what happens if you are doing opposite correlation? Whatever happens for P1, if it is in state 0, the P2 will point to state 1, just like enemy. So this is like friends. So whatever happens for P1, it will show immediately in P2 in the same way. But in opposite correlation, whatever happens for P1, the P2 will show opposite side. Suppose if you are changing P1, to 1, what happens for P2? It will change into 0, opposite. So this is what you asked in previous question. So various types of entanglements are available. One is positive, one is negative. Are you able to get the idea now? Is it clear? Somebody asked that question, right? Are you able to get the idea now? Yes, position. How to say? So try to understand this superposition, entanglement. Look at this. Superposition you can find in one quantum particle. Okay. If you want to create entanglement, you need to have 2 or more quantum particles. Okay. So whatever happens for one quantum particle, okay, the same effect you can see in another quantum particle. So take an example of P1 and P2. So this is particle 1, this is particle 2. If they are strongly correlated, okay, then if you are separating that quantum particle, then what you are doing, you are changing the rotation, you are changing the position of one quantum state. Let's say it is pointing to 1. It is pointing to 1. The other quantum particle also matches the same position, 1. So here you will get confused, means it is a quantum state. It don't say like position. This is quantum state. If quantum state of P1 is pointing to south pole, okay, the quantum state of P1 also pointing to south pole. So this is positive correlation. This is positive correlation. Same way you are able to get the negative correlation. Same way you are able to get the negative correlation. So how we are getting negative correlation means, okay, if two quantum particles are oppositely correlated. So what happens if you are changing state of one quantum particle to upside, definitely the state of the other particle go opposite side or opposite quantum state, opposite quantum state. So don't confuse between position. I am talking about the quantum state. Is it clear now? If you are not able to understand, we'll go by a circuit. We'll go by a circuit. So go for Google Composer, IBM Quantum Composer. So go to this website. So superposition, you can observe that phenomena in single quantum particle. Entanglement, you need to have minimum 2 quantum particles. So to create entanglement, we need 2. So what I am doing, I am having Q0, Q1, C1 and C2. So modify like this your circuit. So we have 2 quantum particle. We have 2 classical register bit. So how many possible combination we have? 4 possible combination. 0, 0, 0, 1, 1, 0, 1, 1. Okay. To observe superposition, what we need to do, we need to implement Hadamard gate. So drag and drop Hadamard gate in Q0. Drag and drop Hadamard gate in Q0. What you will get? You will get 0 sometimes. You will get 1 sometimes. So this is the meaning of superposition. Okay. So two possibilities are there for Hadamard gate. How Hadamard gate will create equal superposition. Sometimes it will generate 0, sometimes it will generate 1. So that is why out of 4 possibility, we got only 2 possibility. 2 possibility for Q0. Q0. Okay. So look for Q1. What is the output of Q1? Always state 0. Always state 0. So how many combination you are able to create out of this? Only 2 combination. So you can combine 0 with 0, 0 with 1. So that is what you are able to observe over here. Are you able to get the idea? So why we got 0, 0, 0, 1? Because these 2 qubits will form only 2 states. So what do you do? Delete this Hadamard gate. What happens? You are able to observe only 0, 0. So Q0 is 0. Q1 is also 0. That is why you got only one possibility, 0, 0. Next, try to put not gate in Q0. The second gate is not gate. Second gate is not gate. So if you implement second gate over here, now what happens? This 0, then we are implementing not gate, turn into state 1. So power supply will happen over here. Now look at the combination. So this is 1 and Q1 is 0. So this is Q1 and this is Q0. So that is why you got 0, 1. All of you able to do? All of you able to do? So we completed 0, 0, empty circuit. If you put not gate in Q1, Q0, then it will become 0, 1. Drag and drop not getting Q1, drag and drop not getting Q1, and observe what happens. Observe what happens. I try to change color. So this is Q0. So what Q0 contains? Stage 0. Okay. So this 0 is mapped over here. And look at this. In Q1, what we are having? Q1 we have 0, but we implemented NOT gate. It is turned into Q state 1. It is turned into state 1. So this is mapped over here. So Q1 is now state 1. So Q0 now it contains state 0. So that is why we have 1, 0. That is why we have 1, 0. So we covered 0, 0, 0, 1, 1, 0. To achieve 1, 1, you need to implement one more NOT gate. To achieve 1, 1, you need to implement one more NOT gate. Now both qubits are in state 1. Now both qubits are in state 1. Now what do you do? Delete this NOT gate. Delete this NOT gate. Implement Hadamard gate in Q0. Now we are able to understand, right? So Q0 contains Hadamard. It contains two possibilities. So sometimes it will generate 0. Sometimes it will generate 1. Okay. So what about Q1? Q1 always generates 0. Q1 always generates 0. Okay. So look at the first combination. Look at the first combination. So this is generated by Q0. This is generated by Q0. Okay. So this is generated by Q1. So what is the Q1 contains? Q1 contains stage 0. So that is why you got 0, 0. Now what I do? I try to change the output of Q0. Imagine if Q0 generates 1. If Q0 generates 1, yes, you can do. So I got 1 because of Q0. So look at the second example, Q1. Q1 always produce 0. So Q1 is 0. Q0 is now pointing to state 1. So that is why you got 0, 1. Are you able to understand why only two states 0, 0, 0, 1? Because we have Hadamard gate in Q0 and nothing in Q1. Look at the third combination. Look at the third combination. What Hadamard gate will generate? 0 sometimes, 0 sometimes, 1 sometimes. But what about Q1? Always 0. Always 0. So look at the possibility of first one. Look at the possibility of first one. So 0 is produced by Q0. But look at the possibility of Q1. So Q1 will not be able to generate 1. So that is why this possibility is impossible. So this one is not possible by Q1. Same way, this one is also not possible by Q1. Are you able to understand why the third combination and fourth combination not able to produce by this circuit? Are you able to understand? So look at the Q sphere pointing to 0, 0, 0, 1. Only two possibilities. Now drag and drop this Hadamard gate in Q1. Now drag and drop this Hadamard gate in Q1. And observe what is happening. Observe what is happening. So try to map. Q0 always produce state 0. Okay. So Q1 sometimes it will produce state 0. Sometimes it will produce state 1. Sometimes it will produce state 1. So look at the first combination. Look at the first combination 0, 0. So this 0 is possible by Q0. This 0 is possible by Q0. Okay. So this 0 is also possible by Q1. So that is why 0, 0 is possible. 0, 0 is possible. Now look at the second combination. Now look at the second combination. So what is the second combination? Second combination is 0, 1. Second combination is 0, 1. Okay. So 0 is produced by Q0, but it is showing 1. So this is impossible. This is impossible. But look at Q1. What Q1 able to do? Q1 able to generate 0. So this is possible, but this one is impossible. So as the whole, this is impossible. I'll clear, you try to understand. So look at the third combination. Look at the third combination. So 0 is possible by Q0 and 0 is possible by Q1 and 1 also possible by Q1. Yes. That is why we got only two combination if we have only one Hadamard gate in one qubit. So try to understand this. This is very important. So this 0 is possible by Q0. This 1 is possible by Q1. So this is also possible. This is also possible. So 1, 0 combination is possible. Now look at the fourth combination. Look at the fourth combination. So what is the fourth combination? 1, 1. What is the fourth combination? 1, 1. 1, 1. So this one is impossible by Q0. This one is impossible by Q0. Okay, the whole term is impossible now. So we covered 0, 0, 0, 1, 1, 0, 1, 1 individually. If you are having Hadamard gate, you will get two possible combinations. Okay. Now what you do? Drag and drop two Hadamard gate. Drag and drop two Hadamard gate in two individual qubit. Now we can see all four possible combinations. Now we can see all four possible combination. So this will generate 0. This also generates 0. Same way, this also generate 1. This also generate 1. So all possible combination you will be able to get simultaneously. So this is the example of superposition of 4 quantum states simultaneously. So at the same time, it is pointing to all 4 directions parallelly, instantly. Is it clear now? Shall we move? Any doubts over here? You can ask me. Okay, fine. Now we need to understand for entanglement. So this is an example of entanglement. We covered about Hadamard gate. We covered about control NOT gate. So if you are placing Hadamard gate followed by control NOT, it will create entanglement. So what is the initial state? State 0, 0. So this is the initial state. This is the initial state. So what happens if you go through Hadamard gate? If you go through Hadamard gate, it will become positive state. So how will you represent positive state? By using this equation. So 1 over root 2 multiplied with state 0 plus 1 over root 2 multiplied with state 1. Okay. Then what happens if you go through control NOT gate? Okay. The whole term will go through state 0. Will go through state 0. So this is combined state. This is combined state over here. So positive state going to react with state 0, you will get combined state. So if you do multiplication, you will get state 0 with state 0, state 1 with state 0. So if C naught going to act on this state will lead to 0, 0, 1, 1. So this is an example for entanglement state. Are you able to get the idea? So I try to explain one more time. We are starting with state 0, 0. Okay, individually we can say, otherwise we'll get confused. We are starting with state 0, 0. So this is the initial stage. I will say step 1. I will say step 1. So step 2, what we are doing? We are doing a Hadamard gate operation on stage 0. So after doing Hadamard, it will go to positive state. So this is equivalent to positive state. Okay. So combinedly, what is happening? Stage 0 going to combine with positive state. So this is step 3, combined state. So positive state going to react with stage 0. Okay. When you add control NOT over this combined state, so you'll get 0, 0, some cases, or 1, 1. So whatever happens for particle 1, you can see the same effect in particle 2. If particle 1 is 1, particle 2 also 1. We covered entanglement, right? So this is a example for entanglement. So this is demonstrated by a scientist called Bell, and this is called Bell state. So note down this. So for this experiment and demonstration, they gave Nobel Prize. So in your quantum lab, okay, you can demonstrate a Nobel Prize experiment. So this is a simple example. So this simple example is a proven mathematical description of entangled state. So we try to do this entanglement state over here. So what is the logic over there? One Hadamard gate followed by control knot. One Hadamard gate followed by control knot. Okay. So we have two possibility. Hadamard gate will generate 0 sometimes. Hadamard gate will generate 1 sometimes. Okay. So we'll discuss two state. Case 1. If Hadamard gate produce 0. Case 2. If Hadamard gate produce state 1. Okay, we'll draw the circuit. So Hadamard gate produces 0. 0 means no power supply. No power supply. Then you have control NOT gate. So power supply will not come down. This NOT gate become inactive. So stage 0. Here also stage 0. Second case, if Hadamard gate produce 1, what it means? Power supply will happen. So this power supply also comes down. So this will enable this NOT gate. So state 0 becomes state 1. So above also state 1, below also state 1. So this is case 1 and this is case 2. All of you able to understand? All of you able to understand? I will repeat once again. If it is not clear, what I will do, I try to draw separately. So we have two qubits, right? We have two qubits. So Q0, Q1. We have Hadamard gate. Okay. Then what we have? We have control knot. Okay. So two cases. Case 1. If Hadamard gate produce 0. Case 2. If Hadamard gate produce 1. We'll draw the same circuit. Q0, Q1. Q0, Q1. Okay. So we have Hadamard gate. We need to implement Hadamard gate. So here also Hadamard gate we have. Here also we have Hadamard gate. Okay. So look at the first case. If Hadamard gate produce 0, 0 means there is no power supply. If there is no power supply, it will not come down. So this NOT gate become inactive. So what is the starting state of any quantum circuit? Stage 0. Okay. If we apply Hadamard gate, if Hadamard gate produce 0, 0 means no power supply. So stage 0 will retain as it is. Because this NOT gate is inactive. So consider here Q0 start with 0, Q1 start with 0. But after applying through Hadamard gate, power supply will happen. So what happens when power supply happens? So power supply will flow. Okay, it will come down. This will enable this NOT gate. Your state 0 is turned into state 1 now. So above also state 1, below also state 1. So this is an example for entanglement. So whatever happens for Q0, you can see the same effect in Q1, positive entanglement. So this is an example for positive entanglement. I hope each and every one of you able to understand this. This is an example for positive entanglement. So 0 means 0, 1 means 1, 0, 0, 1, 1 simultaneously. Okay. So how to go for negative entanglement? How to go for negative entanglement or opposite entanglement? What we need to do? Can anybody able to say? How to change if Q0 is 0 means Q1 should be 1. How to make opposite? It should be 0. If it is 0, Q1 should be 1. So how to change the circuit to make it opposite? See, control NOT gate will create relationship among two qubits. Yes, we can use NOT gate, ma'am, but where to apply NOT gate? Your answer is correct, but where to apply NOT gate? Your answer is correct, ma'am. On Q0, okay, let us do this. Here, you said in Q0, NOT gate. Any change in your output? After H, okay. See, after H, any change? No change. The answer is correct. You need to use NOT gate, but where to apply? On both first qubits. On both means what, sir? Q1. See, try to think in this way. If you apply not getting Q1, then output will become entirely opposite. If Q0 is 0, Q1 become 1. If Q1 become 1, Q0 become 0. We'll go to the same circuit. We'll go to the same circuit. I try to copy paste. Let's see. Yes, able to do so. Thanks a lot. Very difficult to place, where to place. Okay, I try to explain over here. So take an example of Q0 equal to 0. Suppose if Q0 is producing 0, and what we are doing, we are implementing a NOT gate over here. Initial state is 0, 0. So after Hadamard gate, suppose if Hadamard gate produce 0 means no power supply. No power supply means it will not come down, but downside you can see the changes. What is the change? This 0 is turned into stage 1. Okay, the NOT gate is inactive. So 1 will retain as it is. So upside stage 0, downside state 1, opposite to each other. Are you able to get the first idea? Are you able to get the first idea? So look carefully. If first Hadamard gate produce 0, the second NOT gate will produce 1. Suppose if Hadamard gate produce 1, so what happens? Power supply will happen. Power supply will happen. It will come down. This NOT gate is enabled. Okay. So stage 0, stage 0. Here it will turn into 1 because it is turning over here. This 1 is again converted into 0. So the first qubit is 0 means, sorry, the first qubit is 1 means the second qubit is 0. Totally opposite. So that is what happening over here. So you need to place NOT gate in Q1 before entanglement gate or after entanglement. So anyway, it will give opposite output, different output. But if you are placing before Hadamard, no changes, right? If you are placing before Hadamard, no changes. Because Hadamard will create equal superposition. Maybe you're starting from 0, maybe you're starting from 1. It doesn't matter. It doesn't matter. Okay. Now what we do, we try to implement NOT gate over here. Then what we do, we try to implement a Z gate over here. So do this. Can you see any changes over here? What is the change? Please put in the chat box. So I'll select this Z gate. I'll delete this Z gate. Now, if I put Z, what happens? I'll zoom for your convenience. So some changes are there. So place your mouse over here. You can see what is the change. The phase angle will get changed. Okay. So delete this Z gate. And you can see phase angle equal to 0. So it means you can create multiple types of entanglement if you are playing with a NOT gate and Z gate. Okay, you can get a multiple types of entanglement if you are playing with NOT gate and Z gate. So these are the 4 types of entanglement. 4 types of entanglement. So whatever we saw, Q0 is 0, Q1 is 0 means positive entanglement. Okay. So this is positive state. This is positive state. If we are adding NOT gate to second qubit, if you are adding NOT gate to second qubit, you will get opposite entanglement. You will get opposite entanglement. But if you are adding a phase flip, you will get positive entanglement with phase flip. So this is negative state. This is negative state. This is positive state. And this is opposite entanglement with positive state. Okay. This is opposite entanglement with negative state. So we will be able to create 4 different types of entanglement. Be able to create 4 different states of entanglement. So these are called basic Bell states. But what is strange, if we are creating a positive entanglement, the probability of measuring the first qubit is 0 is only 50%. But once you do the measurement, the second qubit chance of the value 0 is 100% now. Okay, look at this strange. The probability of first qubit is 50%. Okay, but the probability of the second qubit is 100% always. Based upon this. If first qubit is 50%, the second qubit is 100% of getting 1. For all 4 entanglement, it is the same. Are you able to understand this? So we'll try to cover one by one Bell states. So this is positive entanglement. So first qubit is stage 0 means second qubit also you will get stage 0. If first qubit is state 1 means the second qubit is also state 1. Is it clear? The first one is clear. So this is 1 over root 2 stage 0 0 plus 1 over root 2 state 1 1. So this is what we discussed over here. Okay. So look at the second one. In positive, you need to change the phase of your gate. So how will you change phase of your gate? Try to put a NOT gate. Okay. Then put a Z gate over here. Or what you can do, you can delete NOT gate. You can place Z gate over here. So this is positive entanglement with phase flip. So this is little tricky. If the output is 1, then only it will change sign of the second qubit. So for 0, you'll get 0. You will get 0 without any phase flip. without any phase flip. Okay, but for one, okay, you'll get the same one but with the negative sign because of Z gate. So note down this point. So that is why you got phase angle only for one state. So if you observe color, you are able to understand this. Are you able to see? So Z gate will not work in state 0. Z gate will introduce pi phase difference only in state 1. Okay, so delete this Z gate, place NOT gate in Q1. Then what you are doing, you are creating opposite entanglement. You are creating opposite entanglement. If you are adding Z gate to this, you will get phase difference. If you add Z gate after this control knot, you will get phase difference for one of your quantum state. So try to play along with this Hadamard gate, NOT gate, control NOT gate, Z gate. You try to understand 4 different set of your Bell states. So last class we covered about Julia. Okay, we covered about Julia. We triggered some issue or error. Okay, today what we'll do, we'll try to redo the same exercise. I'll create new file. I'll try to create new file. So try to install Julia. Try to install Julia. Run this tool. So pip is a command which will install any Python related package at most easy. It will fetch from server. So if package is existing, it will fetch. So I try to install Julia in Google Colab. So go to Google Colab, and try to run this command. I'll share this coding. Next, what we supposed to do, we need to install the quantum related packages in Julia. So copy paste the second command in next cell and try to run. So indentation, give one space. Let's check whether it is working or not. Maybe I need to give enter, then one tab space, give enter, tab space, give enter, one tab space. Okay, This error you can try with go to runtime, change runtime, type, select here Julia. I forgot to mention, so that is why we are getting error. So go to runtime, go to menu, go to runtime, select change runtime. I'll mention in the command box. Go to menu, select runtime option, select runtime, type Python 3 into Julia. So change over here, select Julia. Now save. Now we are able to run. Sorry about that. I forgot that. Are you able to get the output in this way? Okay, good. Sometimes a silly minor mistake, it will hold our result. If you keep on working, we will remember all these steps. Yes, runtime. Please go through runtime. Change runtime type. Select Julia over Python 3. Then click save. Then execute this command. Okay. So once it is executed, you can look for the next command. What is the next command? Init using your plots. Now the packages, if you want to visualize your quantum circuit, you are able to do with using U or UPOP. So likewise, we can create a library package in Julia and we are able to upload in their project if they are approved. Still it is executing, I think so. We need to wait for some time. So if you are able to execute, I will share the next command for you. Okay. So we are creating two quantum Fourier blocks. Two quantum Fourier blocks. I already shared in your Canvas account. Please go and check. Now it is getting started to execute. So we created two quantum Fourier transform blocks, and we are able to chain that. Okay, we are using a chain function for that. So run one by one. You are able to execute. So no need to wait for execution. Then for displaying some output, we need to install some packages. I'll share the packages. So troubleshooting this will take some time. So whenever you got any error, please try to do Google, okay, refer multiple sources, then try to clear those error messages. So if they are changing anything in background in software repository, we'll get lot of error. Finally, if you are able to do all this stuff, you're able to see your quantum circuit, what you generated. So it took me 3 hours for me to identify what type of error, what are the packages required for that to clear the dependency, right? So we should not give up, right? Whatever the error appears, we need to search, we need to rectify. Format is showing some error. Why? Okay, anyway, you are able to get the output if you follow this step. Already I shared this. If it is working over here, definitely it will work for you. So don't worry about that. Some of you able to get the output like this plot? Some of you able to get the output, or everybody is getting error? Somebody got output, right? Okay. Anyway, we are able to run. No issue. So I will stop it here. If you have any doubt related to cube rate, you can ask me. Now it is taking so much of time for maintenance. Sorry about that. Any doubts? Put in the chat box. I try to answer. Related to control node, related to build state. Explain 4 types. Okay. So this is positive entanglement. Positive entanglement is first qubit is 0. The second qubit is also 0. If first qubit is 0, the second qubit is also 0. If P1 is 0, P2 is also 0. Okay. If P1 is 1, P2 is also 1. If P1 is 1, P2 is 1. Okay. So this is related to positive state. Next, if you're adding a NOT gate, between two qubits, what happens? It will make contradictory. If first qubit is 1, the second qubit is 0. If first qubit is 0, the second qubit is 1. Okay. In same way, if first qubit is 1, the second qubit is 0 by adding NOT gate. Okay. If you're adding a Z gate, what happens? It will introduce a phase difference, so which is called negative state. If you're adding NOT gate along with Z gate, you'll get negative correlation with phase flip. So this is NOT gate. Maybe I have one more slide. It will help you. Use build states. So look at this. Are you able to get the idea? I'll close this. So we have Hadamard gate in Q0 followed by control node. What is the combined state we got? State 0, 0, state 1, 1. Okay. So what we are doing? We are adding a Z gate. Okay. Either in Q0 you are able to put or Q1 you are able to put, you will get a phase flip. So this is positive correlation with phase flip. So there are two combinations, right? There are two combinations. If Hadamard gate produce 0, then Z gate will not do anything. But if Hadamard gate produce 1, it will do phase flip. It will change into -1. That -1 is resulted over here. Minus. What is the case of Bell state 3? We have NOT gate, where we are putting NOT gate in Q1. So this will contradict between Q0 and Q1. If first qubit is 0, the second qubit is 1. If first qubit is 1, the second qubit is 0. Okay. So remember these three circuits. Add a Z gate to that. Add a Z gate to that. You'll get Bell state 4. So opposite entanglement with phase flip. Now we are able to get this idea. Is it clear now? I'll share all this PPT. So sometimes what you'll do, you will restart your Google Colab, you'll get the output. So if you are starting to restart your kernel, you will get the output. I'll share all PPTs, don't worry about materials. Tackling error is somewhat challenging. So restart your kernel, definitely you'll get output.
Thank you so much, sir. Participants, I think plenty of discussion has already been done. So I hope the query has been resolved. But still, if you have, you may put it in the chat box. Else, one small announcement is there. Tomorrow we will be having quiz 2 also. I mean, along with quiz 1, we will be opening quiz 2 also. Okay. So be informed and try to convey this information to your colleagues who have missed basically the previous quiz 1. Okay. So be prepared. And thank you so much, Jay Kumar sir, for this insightful session. And
Thank
I
you,
would
sir.
also
Thank you. Thank you all.
like to thank all the participants for joining this session. So good day to all. Thank you all.